Hi. In the previous video, we've started limits. We've introduced the concept of a limit, and what I wanted to show you now is the graphical illustration of limits, because this is actually what is showing us how the limit actually works. Okay, so look, we will always be considering some functions. Q equals f of v. Well, it's like, but you still can think of it as this is y, this is x. Nothing would change. Well, we've just changed the notations for limits. We will go back to regular notations a little bit later, but there's a point to it, so let's maintain it. Okay, so we said that the function possesses a limit if limit from the left-hand side, from left side limit, is equal to limit evaluated from right side. Then we say the limit with v approaching some n of q is equal to some l. Look, how would we see this on a function? So look, we've got some arbitrary value chosen over here. We can do it for any point in the domain of the function, of course. And now we see that the exact value of the function, so f of v, over here is equal to l. Okay, so now how can we imagine evaluation of a limit? Look, if we are approaching n from left-hand side, this means that we are considering values that are lower than n, but they are getting closer and closer and closer and closer to n. And look, now we need to see what is happening to the values of the function as n is increasing. And look, we see that the line is going in here. It's getting closer and closer to this point. Now, when we evaluate a limit from right side, it means we are starting with the values that are bigger than n, and we are moving closer and closer and closer and closer to n. Now that we see what is happening to argument, we need to see what is happening to the values of the function. And look, here we are starting. We see the values are getting lower and lower and lower and lower, and we finally end up at this point. And look, what we see over here, that when we evaluated the limit from the left side, and we were getting closer and closer to this point. When we were evaluating the limit from right side, we're getting closer and closer to this point. And look, this indicates that doesn't matter from which side we evaluate the limit, we always end up at the same point. And it turns out that in this case, L is actually the limit of this function. So in this case, we can say limit at n exists, and it's equal to the specific value L. Okay, but look, we can have different cases in which we evaluate limits. Look, it's not always that the arrows so nicely point to this specific point. Okay, let's consider a function like this. Well, how could we describe this function? For example, this could be an upside down parabola, right? Or it could be a part of some polynomial function which has a lot of hills and valleys. But of course now we are interested in what is the limit at this arbitrary point n. And look, again, we would start from the left. So we are starting from the values that are lower and than n, but are getting bigger and bigger and closer to n. And now we can observe what is happening. What is happening to the values of the function. And we see that as n is increasing, on the graph we see it as getting closer and closer and closer to this point over here. Now, if I'm going to move on v, so on our argument from the right side to n, so we are starting with bigger values, but we are moving closer and closer to n. What is happening to the values of the function? Well, we see that they are increasing, they are going up and higher and moving closer and closer to the left. And look, again, we ended up in the same point. So all the arrows over here are pointing to the exact same location. What does it mean? Again, left side limit and right side limit are equal to one another. So the limit with v approaching n out of q exists, and it's equal to the value of the function at this point, which is L again. Okay, how about this case? No, this is very similar case, but now look, we have this sharp top at the beginning. How could we obtain a function like this? Well, through absolute value. Look, let's do a simple case on how can we end up in a situation like this. Let's just say that we've got a function q is equal x minus plus 2, right? V plus 2. Okay, so how would I draw this function? Well, this is a simple linear function. So it would look like this. We would go through 2 over here and like that. Okay, and now what would happen over here if I would, for example, impose an absolute value on this function, right? Now, look, if I impose absolute value, everything that used to be positive stays positive, but everything that used to be negative is going to be reflected above the v-axis. So we would get a function that looks like that. Now, if now I would impose, for example, a minus in front of this absolute value, what would happen? Everything that used to be positive becomes negative. So now the function would look like that. And finally, if I, for example, would add maybe a different color, add 3 over here, I would have to move this function 3 units up. Look over here, we've got -2 because here is 2, so here needs to be -2. So it would go through 1 and it would look like this. Okay, and look, through this, we actually obtained this shape. And look, I'm using this specific case because this case will constitute a very important exemption of the general rule that we're going to use when we're going to be calculating derivatives. But let's go back to the limit. So we know how to get this function, we know how it looks. So let's evaluate the limit. Well, again, we start from left side limit. So argument is getting closer and closer to n. And we see that at the same time q, so the value of the function, is getting closer and closer to this point. Now, if I'm evaluating a limit from right side, argument is bigger than n, but it's getting closer and closer to n. Again, I see that these arrows are pointing to the same point. So what happened here? Again, we have a case. In which this point is a limit of this function. Okay, but look, of course, it's not like that limit always exists. Look, if this would be the case, then probably we wouldn't have to go through all this trouble with evaluating left side limit and right side limit. So now let me give you two examples of the cases where limit does not exist. Look, what we see over here is called a step function. And look, this step function could be written as q is equal to. And look, here we see that actually this function takes only two values. Well, assuming that the function continues like this indefinitely to negative infinity on v, and here continues like this on positive infinity on v. So look, here we see this function takes two values. L1 if or for v that is lower or equal to n, right? On the other side, we've got this point, and we've got the value of this function is equal to L2 for v that is bigger than n. And look, of course, from the inequalities over here, where here we have lower or equal to, we get that this point is associated with the value L1, while over here we've got this open circle. No, actually, when we say about a circle, it is open. And over here, this point, so only after this point, the value of this function, so q, turns into L2. Okay, so knowing this, let's see, let's just see how our evaluation of the limit is going to work here. Okay, look, here we have a case. Okay, again, we start with evaluating the limit from the left side. So we start from v lower than n, and we're getting closer and closer to n. Look, now we can see that the values of the function, so q, is getting closer and closer to this point. Now, if I'm going to evaluate right side limit, so look, from the first part of the exercise, we get that this point over here could be a candidate for a limit. But now, let's go to the right side. We start with v higher than n, and we are getting closer and closer and closer to n. Now, value of the function here are values of the function are given by L2. Look, as I get closer and closer and closer over here to n, this points me to this point, right? It's like this point would be a limit. So look, in this case, I could write that limit evaluated from the left side is equal to L1. On the other hand side, on the other hand, limit evaluated from right side, Q, is giving us L2. Those two are different. So, in this case, actually, limit does not exist. Okay, so now that we saw an example of the case where limit does not exist, it should point you in the right direction. Because look, we clearly see that in the cases where we have some breaks in the function, so we cannot like draw them without picking up our pencils, maybe we will deal with the situation where limit does not exist. But there is a second point. There was this open circle. Now, how do we deal with that? So now let's move to the function that we see over here. Look, here we've got a case that, again, as before, Q is some function of V. But look, we see that here is an open point, right? So there's nothing in here. Why? Because in this case, the domain of the function is equal to real numbers, but without n. Okay, so how do we approach a case like this? Okay, let's start in the same way. Let's start by evaluating left side limit. And we see that the values of the function are pointing us to this, to the middle of this circle. Now, if I evaluate the limit from right side, now the values of the function again point us to this circle. So, does the limit exist over here? Actually does. And look, because regardless from which side we've evaluated the limit, we've ended up in the same point. But you might say, yeah, but this point is not part of the function. Look, we were not discussing whether the limit, we never said the limit needs to be the part of the function. It doesn't need to be. Even though this point is not within the function, this point is still a limit of this function. And as you will see, we will have plenty of examples of the cases where the limit of the function is not a part of it. And actually those are the most interesting cases. Okay, now, thus far, we are only interested in evaluating limits at some point n. But of course, this point could be any point in the domain. So if we know how to do it for one point, basically we know how to do it at any other point. But of course, there are two special cases where this does not. Where this does not. Although, you know what? Let's try one more case. Let's try one more case. Why not? Okay, now let's see. Let's say that we've got another function. And this function looks like this. Okay, we assume it's of course going here, it's going here, it's going here. Did we see this function somewhere? Yeah, of course. This is a reciprocal function that was moved up and to the right. Okay, and again, let's say that we want to evaluate the limit of this function at n. Okay, so first, let me start by evaluating the limit of this function when n, from the left side. So when v is getting closer and closer to n, but with lower, but from the values lower than n. Okay, now we can look what is happening to a function. If I follow the function, where am I going? Well, I'm going lower and lower and lower. And look, if I would be getting closer and closer to n, it would actually go where? Into negative infinity. So look, at this moment, right at this moment, we can say that definitely this function does not have a limit at n. Why? Because if I evaluate limit with v approaching n from the left hand side out of q, I'm getting as a result negative infinity. And look, we said that L needs to be a finite number. It cannot be either infinity or negative infinity. So we already see that there is no limit at n over here. Okay, but even though there's no limit at n over here, let's see what happens on the other side. So, if now I'm evaluating right side limit, I'm getting in closer and closer to n from v bigger than n. And look, let's see what is happening over here. We are getting on the function higher and higher and higher and higher and higher. How can we, so where will we gonna end up? We would be going further and further up, and we see that the values of the function are getting closer and closer to infinity. Well, maybe not the best choice of words, but they are going to infinity. So look here, we have the right side limit, so with limit with v approaching n from the right side is equal to infinity. Okay, look, we can have different combinations of cases like this. Okay, so what if we've got a function that looks like that? let's think what formula would give us function like that. We should also remember that we can get a function like this. Let's just say if we have q equal to 1 over v squared, right? Because here we see that we would get a reciprocal function, but if v is in the second power, all the positive values turn into negative values turn into positive, positive stays the same, and the curvature of the function changes slightly. But look, we also see that this function is not coming from here, but somewhere over here. So what would I have to change here? Well, I need to just move v by n. Remember, when we subtract, we go to the right. When we add, we go to the left. And look, so we can conclude that this point is n. Okay, and let's evaluate limit over here. So we see that if I'm getting closer and closer to n from the left side, values of the function are getting bigger and bigger and bigger and bigger and bigger. Now, if we would so we can see that the limit here would be positive infinity. So now, if I'm going to evaluate the right side limit, so I'm getting v is getting closer and closer to n from but from above, we see that the values, so the q is getting closer, is getting higher and higher and higher. So it's also the limit here is equal to infinity. But remember, even though in this case one condition for the existence of a limit is fulfilled, so left side and right side limit are the same, still this is not a finite number, right? This is infinity. Still, in this case, just like over here, limit does not exist. And look, if I would now, for example, to this function and add minus up front, what would I get? Well, I would get exactly the same shape, but a mirror reflection the function would go below the horizontal axis, right? Because everything used to be positive, but I put minus up front, everything became negative. So now the function would look like this. Now, I hope you can see it right away that if we're going to evaluate limit at n from left side, we see that the values of the function are getting lower and lower and lower. They go to negative infinity. Over here, if I evaluate the limit from right side, we see that the values of the function are getting lower and lower. So in this case, limit with v approaching n from left side is equal to limit with v approaching n from right side, and it's equal to negative infinity. But again, we can clearly state that limit does not exist, because even though those limits appear to be equal, still limit is not finite, and as long as it's not finite, so it's not a given constant number, the limit does not exist. Okay, so now we've considered here plenty of cases where we were approaching, when we were evaluating the limit at n, some particular number n. And we already said that if we can do it for one point n, we can do it for any other point n. We can do it graphically, like we did it over here, although usually it is better and more precise if we are doing it on the formula that is giving us some function. But now we need to take into consideration two cases that do not fall into the category of a constant number. Well, and those two cases are, of course, limit with v approaching negative infinity and limit with v approaching infinity. And look, as we said in the previous video, infinity can be approached only from the left-hand side, while negative infinity can be approached only from right-hand side. Right, so now we have we need to do half of our work, but because of that, let's just evaluate both of those in the cases we are going to consider. Okay, so let's start with the function. It's gonna look like this. Okay, let me draw an asymptote, maybe a little bit higher. And let's just say that this function looks like this. Okay, and let's just say that we know what is this asymptote. It is equal to some L1. Okay, now, have we seen a function like this before? Well, we see this is an exponential function. And let's just say that in this particular case, this exponential function has the form of q equals to e to the power of v, but it's not enough, right? So, because this function is L1, has an asymptote on L1, so we can include it's plus L1. I did it to make things easy. Okay, and I hope you can tell me how much do we have at this point? Very good. This is L1 plus 1. Why? Any number, any positive, well, any number, for now, to the power of 0, except, of course, 0, is giving us 1, plus, we need to add L1, so this is how we end up over here. Okay, and now, let's do two things. First, let's evaluate the limit of this function with v approaching negative infinity. Okay, and let's just do it graphically. Okay, so look, now we have a case that values of the function, arguments of the function, are getting lower and lower and lower, and then they never cease to decrease, which means that they are ever decreasing. We are going into negative infinity. Now, let's see what happens with the values of the function. Look, if I follow this function over here, we see that this function is getting closer and closer and closer and closer to L1. Will it ever reach it? Well, no. Look, doesn't matter. how big, how small, I'm sorry, is going to be V, then E will never get small enough. Look, remember that if V is negative, it means we are dividing by, let me give you an example. If we have E to the power negative 1 million, this is the same as 1 divided by E to the power of million. And this is a very, very big number. But look, is it 0? No. But look, now if we have a billion, we are dividing by E to the power of billion. Then we will have a trillion and quadrillion. We are dividing this one by bigger and bigger and bigger number. And look, you can think about it like this, that this expression over here is getting so tiny that it's barely visible. But look, doesn't matter how big is going to be this exponent, we will always have something. But what is the limit there is the value to which we are getting closer and closer and closer to. And look, as V becomes infinitely, is becoming smaller and smaller and smaller, so it's getting to a negative infinity, we see we are almost at L1. And L1, in this case, is our limit with V approaching infinity, negative infinity. Okay, so now let's go to the other case. What if now I want to evaluate limit with V approaching infinity out of Q? So, now I'm simply moving in the other direction. So I'm moving here. So now imagine, as before, that V is taking incredibly big values. Now we've got E to the power of quadrillion. But then it's going to get even bigger and bigger and bigger and bigger and bigger and bigger. Now, will it ever stop growing? No, right? So we have, as V is getting bigger, this entire expression is getting bigger and bigger and bigger, which means that the limit here must be infinity. Okay, so look, what we've learned from this example, that limit with when we have limit with V approaching negative infinity or infinity, can be either infinite, in this case we say there's no limit, right? Or it can be some number. And look, this case with the number, we have over here, the limit exists. Over here, the limit does not exist. Look, you can imagine it like that. It's like, is it possible to put some value, doesn't matter how big, and the value of this function will never reach this value? No, it can't. So the function is boundless or limitless, if you might say, as you might say. So it does not have a limit with V approaching infinity. And look, we could reverse this situation. For example, look, I could make a very tiny upgrade to this function. I could add minus in front of V. Now, how would this function look like? I hope you remember that if we put minus on an argument, we get a mirror reflection with respect to vertical axis. So what we are receiving is going to look like this. Okay. I should start with drawing the limit. I thought I'm going to do better, but I always tell you to start. I always tell you to start with an asymptote. I didn't do it, and let's see, and you can now see how it ended up for me. Okay. So here we have Q, here we have V, here we have some L1, and still here, negative V. If I replace V with 0, doesn't make any difference. I will have here L1 plus 1. Okay, so again, let's evaluate the limits. Look, here situation is simply reversed. If now, I'm going to start by evaluating right side limit. I see that the values of the function are getting smaller and smaller and smaller, but they stabilize, right? They're getting closer and closer to a 1. So here I can write the limit with v approaching infinity r cubed is equal to L1. On the other hand, if I'm going to move now into negative infinity, I see that values of the function are ever growing, which means that here there's no limit, because limit with v approaching negative infinity out of q is infinity. Okay. So now let's consider a simpler function. Let's consider a function like y. Oh, okay. Let me just erase the blackboard. We'll just erase the blackboard. And let's say that we've got a function like q equals to v plus 1. Okay. So here we have q, here we have v, and the function is going to look like that. 1 over here. Okay, and I think we can do it now very fast, right? Because it's not very problematic. What would be the limit of this function with v approaching infinity? Well, as v is getting bigger and bigger and bigger, we see that q is getting bigger and bigger and bigger as well. Will it ever stop growing? No, right? So limit here with v approaching infinity is equal to infinity. Now, if as v is getting lower and lower and lower and is getting to negative infinity, we see that the values are ever decreasing. So limit here with v approaching negative infinity up q is equal to negative infinity. But look, we could have the same case if this function would not be linear. If this function would look like that, we could still observe that as v is getting smaller and smaller, q is getting smaller and smaller as well. So again, we would have v with v approaching, limit with v approaching negative infinity out of q would still be negative infinity. And in the opposite direction as well. As v is getting bigger, see the values of the function are ever growing, so the limit must be infinity. And of course, if I would change something in this function, for example, now I would add minus in front of b again. Q equals negative v plus 1. Then the function would look like that. And what do we see over here? Now, as v goes to negative infinity, values of the function are growing because q is getting bigger and bigger and bigger. So, limit with v approaching negative infinity out of q is infinity. And when we look in the other direction, so as v is getting bigger and bigger and bigger and bigger, we see that q is getting smaller and smaller and smaller and smaller. So in this case, we've got the limit with v approaching infinity out of q is negative infinity. And look, again, the function doesn't need to be linear. If the function would be curvy, we would see the same thing. Look over here, as v is going to infinity, we see is going to infinity. Q is getting lower and lower and lower. Here my drawing is very bad. I'm sorry. Here it should be more like this, and here you can see that as v is becoming smaller and smaller and it's going to negative infinity, values of the function, so q, are getting bigger and bigger, so the limit is infinity. And look, this small set of examples actually deals with most of the cases, and now I hope you can imagine limits way easier than before, which will allow you to understand them a little bit better. Okay, look, in the next video, we're going to go back to the formulas, and I'm going to show you how to evaluate a limit of the function based on the formula, so without resorting to graphs. Thank you for your attention.